Hello everyone. Here I will introduce our paper Accept to CVPR, VecFontSDF, learning to reconstruct and synthesize high-quality vector fonts via signed distance functions. Font design is of vital importance in the digital content and modern printing industry. Traditional vector font designing process relies heavily on the expertise and effort from professional designers, setting a high barrier for common users. This paper proposes an end-to-end trainable method, VecFontSDF, to reconstruct and synthesize high-quality vector fonts using signed distance functions. Specifically, based on the proposed SDF-based implicit shape representation, VecFontSDF learns to model each glyph as shape primitives enclosed by several parabolic curves, which can be precisely converted to quadratic Bezier curves that can be widely used in vector font products. What's more, we use the true SDF values as a strong supervision instead of only raster images to produce much more precise reconstruction and synthesis results compared to previous SDF-based methods. The proposed VecFontSDF can be flexibly integrated with other generative methods such as latent space interpolation and style transfer. Recently, several methods based on sequential generative models have been reported that treat a vector glyph as a straw command sequence and use recurrent neural networks or transformer to encode and decode the sequence. More recently, Deep Vector Font was proposed to use dynamic learning to alleviate the problem, showing state-of-the-art performance on this task. Despite using richer information of dual modality data, it still needs repetitively random sampling of the synthesis results to find the optimal one, and then uses CVG to refine the vector glyphs under the guidance of the generative image in the inference stage. Another possible solution to model the vector graphic is to use implicit functions, which have been widely used to represent 3D shapes in recent years. BSPNet uses hyperplanes to split the space in 2D shapes and 3D meshes, but it generates unsmooth and disordered results when handling glyphs consisting of numerous curves. We consider glyph C to be a set of NC counters Ci, and each Ci is defined as a sequence of Bezier curves. To generate practical vector font libraries, our model adopts the quadratic Bezier curves B, which is defined like this. Given a point Pxy, we need to find its nearest curve B hat and the corresponding parameter T hat. After obtaining T hat, we can calculate the distance value and its sign, where Vt denotes the derivative of Pt. Finally, the sign distance is computed like this. Our model aims to generate a set of parabolic curves which are defined by K, P, Q, D, E, and F. We propose a pseudo-distance function of a sampling point to a parabolic curve like this. Then we need to compute the intersection of NA areas to get a shape primitive Fi, and we get a proposed pseudo-distance field by G. After obtaining the final pseudo-distance field G, we need to render it to the raster image in a differentiable manner like this, where gamma represents the learnable range of SDF values. The image reconstruction loss is defined as the mean square area between the reconstructed image and the input image. The rasterization process is shown in this page. We have two types of pre-calculated SDFs, grid SDFs and counter SDFs. Grid SDFs means that the sampling points used to calculate SDFs are located at all grid positions. Counter SDFs means that the sampling points are uniformly distributed near the counters of the input glyph. We only calculate the SDF loss when they have different signs, which means the predicted curves and the ground truth curve are on the opposite side of a sampling point. The grid SDF loss is defined like this, and the counter SDF loss is similar. To further improve the quality of reconstruct images, we also introduce the regularization loss to our model. Specifically, we first need to normalize the parameters p and q to force the square of p plus the square of q equals 1. Then we restrict the minimum value of the square of k output by our model greater than a predefined value to obtain a clear image. The regularization loss is defined like this. Finally, the complete loss function of our model is defined as the weighted sum of all above losses. Then we need to convert the parabolic curves generated by our SDF decoder to quadratic Bezier curves. For each primitive, our initial canvas starts from a square, and each curve splits the space into an inside region and an outside region. Then we calculate the intersection of the inside region of newly added curve and the current canvas to to update the canvas recursively to get the final primitive. Finally, we assemble all the primitives together to form the output vector glyph. Next, I will show the experimental results of our paper. The loss curves of our model evaluated on the test set when training with different losses shows that the grid SDF loss provides a much stronger supervision. Moreover, introducing the counter SDF loss further improves the model's ability in the inference stage. The qualitative results and quantitative results verify the effectiveness of each proposed loss. This page shows the vector font reconstruction results of our method on the test set and the corresponding glyph counters after post-processing. We compare our method with two other existing SDF representations, BSPNet and another implicit glyph shape representation, IGSR, in TVCG. Since the original image resolution used in these two methods is 64, for fair comparison, we also resize the resolution of our input images and the size of sampling grid to 64. We can see that BSPNet only uses straight hyperplanes, which performs poorly on glyph images containing a large number of Bezier curves. IGSR uses the general conic section equation, which cannot be precisely converted to the quality Bezier curve. Quantitative results of different methods further demonstrating the effectiveness and superiority of our VecFontSDF. We also compare our method with two recently proposed vector reconstruction approaches, M2Vect and multi-implices. M2Vect tends to be stuck in local optimums for glyphs with multiple concave regions. Multi-implices results in finer details than M2Vect, but both of them exhibit unsmooth edges and rounded corners. What's more, M2Vect produces hundreds of cubic Bezier curve control points to compose the glyph counter, while most of them are redundant. Multi-implices even need to find thousands of points on the zero-level set of 2D SDF to vectorize the output. We also conduct experiments on vector glyph interpolation to further improve the ability of our representation. This page shows that our model achieves smooth interpolation between different styles of fonts and is capable of generating visually pleasing new vector fonts by only inputting raster glyph images. To further demonstrate the potential of our VecFontSDF for vector font generation, we directly extend the popular few-shot style transfer task from the image domain to the vector graphic domain. This page shows the network architecture. We compare the performance of our few-shot style transfer model with deep VecFont on our test set. Due to the difficulty of handling the long-range dependence, deep VecFont faces serious shape distortion problems. On the contrary, our method simultaneously outputs all the parameters of parabolic curves, which effectively avoid this issue. In this paper, we presented the novel vector font shape representation that can be translated to commonly used qualitative Bezier curves. VecFontSDF uses the true SDF values as a strong supervision in vector font reconstruction, but our method sometimes synthesizes inaccurate vector glyphs for some strange shape. It is also a tough task for VecFontSDF if input glyph images have a lot of disconnected regions. In the future, we are planning to upgrade our model by utilizing more effective network architectures and extend our pseudo-distance functions to higher order curves. Thanks for your watching.